All right. Welcome back. Mm, just trying to get this. Okay. Once again, welcome back to the stream. My name is Wilfred, and today we are going to be solving some data structures and algorithm questions. Yesterday I worked on a few questions. I think I did a two-pointer question, which is this count pairs whose sum is less than target. I'll be repeating this question once again, explaining and going through the code. Then we'll move on to other questions, right? I prepared the list today, so here's my list. I can increase this a bit. Yeah. All right. So here's my list. We'll have a look at some of these questions, and yeah, so we'll do all of that in like an hour. So here, so this is another question we'll solve. We'll be looking at some other, let me see. Yeah, we'll solve a tree question today as well. And yeah, so let me check. Before I start, I will check the chat and see if there are a few people. Okay, there are about 5 people in the chat now, 6 now. Hey, hello, Ransom. Um, yeah. You're doing math. Okay, that's really nice. I think math will help you a lot when you start, doing data structures and algorithm questions. Anyways, it's nice having you guys here. So we'll get started and solve some questions. But before we start solving new questions, I would like to go back to some questions we've seen before. So here's a question I solved yesterday. I will go through it once again to understand what the question is about and the ways we can solve this question. So this question is a pointer related question, right? You can see 2 pointer. There's a binary search and there's sorting. So which is already good, but let's read the question and see what it is. So this is lit code 2824. Count pairs whose sum is less than target. Given a zero indexed integer array norms of length n and an integer target, return the number of pairs ij where 0 is less or equal to I is less than j is less than n being the length of the integer array, and nums at I plus nums at j is less than the target. So here is our input. So we have an example here, right? So here is the nums and we have a target as well. Now, one thing I noticed about solving questions like this on Let's Code is when you see a question that basically is asking you to get pairs of numbers in an array of integers, right? What you usually do, what the question is actually expecting you to have is a pair of numbers regardless of where their index is, as long as the index of I is less than j. It doesn't matter if your pair has you know I in every pair, right? Number at I in every pair that you make with a different j, right? If you look at this example here, you see I is here, I is 0, I is 0 here, I is 0. You can see I appeared a lot of times, right, in these pairs, and j is different, right, each time. So as long as j is superior to I, you can find I and then pair I with any other number as long as that value is superior to I. So meaning for you to do something like this, you will need to first of all sort the array to be sure that every value you have at the beginning, right, is less than the subsequent value or the following values. And after sorting, you can use a two pointer method to quickly search for the values that fall into this condition, or that follows these conditions, right? We have this one here, and this is second condition. So I'll show you how to do that now. First of all, let's go to the board. I always showcase my explanation on the board here, so we'll make use of the board now. Where's my... okay, so we are given, this is not the question, this is the question here. So we are given a zero indexed array, right? In other words, an array with integers in it. So we can take this value, right, and let me write it out. So here is what we have. This is going to be, you know what, before I start writing, let me check if there are any questions to begin with, because I will not be able to check the chat when I start explaining. So refresh. Hello Dan, hello, nice to have you here. Okay, so there are no questions, and I can close this chat now and start my explanation. Okay, so here's what we have. All right, we have this, our input. Our original input was like this. So we have -1, -1, I think 1, or was it 2, 3? Yeah, 1, 2, 3, and 1. So -1, 1, 2, 3, and 1, right? So, like I said, when a question is asking us to find pairs of numbers, right, in an array of numbers, we want to, first of all, understand how the pairs will be formed. Are we looking for pairs of numbers that are, next to each other? In other words, I think it's called there is a word for this, right? Maybe we should just say consecutive numbers, right, in the original array. If that wasn't specified, then there is a chance that we need to sort the array and then choose every subsequent pair to our first number. So let's say a brute force way to do this, right? Let's just imagine it. So let's say we want to write a brute force solution for this question without knowing whether we should sort or not, right? So a brute force way to do this is to first of all start with this number and then pair it with every other number, right? With every other number, as long as first of all this number here, right, plus the second number is less than the target. Already we know that every number in the array, let me remove this, every number in the array has a specific index, right? So if this is 0, 1, 2, 3, and 4. Now, if we choose this number as our first I, then we know for sure every other number after it has a larger index than the chosen number, right? So if we chose this -1 as our first pair, we know -1 is at index 0. So the next number we can choose here is going to be 1, right? It's going to be the next number after it, which is 1, which is okay. Our target here is 2, right? So let's keep that in mind. Now, if this plus this is less than this target, then we know for sure this is a valid pair, right? So -1 plus 1 is going to be 0, which is less than the target. So this is a valid pair. And we'll have to do this for every, we'll choose every -1. We'll choose a pair for every, we'll choose a pair for -1 for every other value less than, superior to 0. So meaning after choosing this one, we have to choose 2. Then we have to choose 3, and then 1, which is the last number in the array. Then we'll do the same thing for 1 again, right? We'll start from this point and we'll pair it with every other value. And we'll do this until we reach the end of this array here. right? Until it gets to the point where we can no longer find a pair for um, for any chosen I value, right? But the problem with this is we'll have to run a separate loop to find every additional pair for this I that we chose, right? So again, we are going to choose I. We know our pair is going to be number at I, let's say num at I, and then num at j. So this is what we have to do. Now we already know that our j is going to be every value after I, which automatically makes it superior to I, right? So if we use a brute force solution to solve this, we are going to end up with a time complexity of O of n squared, right? Which is not really efficient. So what do we do to at least improve uh, our search for the pairs, right? The pairs that we are looking for. Well, for us to do this, we can actually use a two-pointer method. Now, how do we use the two-pointer method? With the two-pointer method, all we need to do is to first of all sort the array so that we are sure that for every chosen value, for every first value we pick, right? For every first value we pick, every subsequent value is superior to it, right? So meaning the larger values are towards the right and the smaller values are on the left. So with the way this array is currently, we don't have any particular order for the integers in the array. You can see, maybe you can argue, oh, there is -1 here, right? And then every other value here is superior to -1. But at the end of the day, we can see another one here, which is less than 3. So this means the array is not sorted. Every integer in the array is just in a scattered position. So what we do to properly efficiently solve this, at least improve the time complexity for our solution without using a brute force solution, is to sort the array. Now sorting takes time, right? Sorting will take, I think, O log n, right? O log n. So this is also another factor, but like at least it is better than you know our brute force proposed solution. Now, this is not directly related to the answer we want to return at the end of the day. This is just the time complexity it takes to sort our array, right? So when we are sorting the array, when we sort the array, we'll end up with something like this. We'll end up with -1, 1, 1, 2, 3, right? This is the sorted form of our array. Now we'll be able to use a two-pointer method to quickly find the pairs. Now we'll find the pairs at the same time, right? We will not use a separate loop to find the first pair and then start looping again to find the second pair. So here's what we do. So first of all, we'll put a left pointer here and a right pointer at this position. Now this is typically how a two-pointer method works. It's a form of, I would really say it's like binary search, but without finding the midpoint, because the value we are looking for has to be a value that makes up for the condition here. We need to find a value where the sum of those values are less than the target. Already we know so instead of using left and right, I'll use I and j so that it is not confusing for us. So let's put I here. I'll just leave it like that, I and then j. So we already know I is less than j, right? Given the way we positioned the pointers. So what we do next is to shift the pointers depending on certain condition. Like for instance, if we find a value, right? If we do the sum of the value at I and j, so we'll say num at I plus num at j, right? The answer we get should be less than our target, which is t here. right? So we'll do this again. So we say -1 plus 3, right? -1 plus 3 is 2. So our current answer here is 2. So what do we do in this case? We know for sure 2 is the same as our target. It's equal to our target. So meaning 2 is on the high end. We want values that are less than our target, right? So for with the way two pointers method work is we ensure that when a higher value is found than our target, we shift the j pointer instead towards the left, towards the part where there are smaller values. If we're looking for higher values, then we'll have to shift the I pointer here. But in this case, we have to shift j. So we shift j from this position to this position here. Now we'll find the sum of the values between I and j, right? So again, in this case, I will erase this part. So we'll take this again. So num at I is -1 plus num at j is 2. So -1 plus 2 is 1, right? So now we have 1. Now 1 is less than our target t. T is equal to 2. So meaning this pair is valid for us to, begin counting how many pairs we've seen so far that satisfy this solution. So we'll write this down: -1 and 2, right? This is a valid pair. Now one thing we also need to do here is how to begin the count, right? How to start counting. Now for this case, for this method of solving this question, we won't increment the count by 1, right? Normally with our brute force solution here, in this case, we count up, right? We count up by incrementing the count by 1 for every pair we found, right? Plus equal 1. So this is what we do in this case. But in this case, we are using a combination of two pointers and a binary search to find that value. So counting the pairs will no longer be the same as our brute force solution here. So how we count the pairs is to find the distance between the left or the I and j, right? At this point, we know for sure, right, every other value going down, right, will always meet up with this condition here, which is the sum has to be less than the target, right? So if you look at this, right, so -1 and -2, if we do this again, if we say -1 and 1, right, if we move this j towards this point, right, if we move j here, we'll still have the same thing, right? This is -1 and 1. -1 plus 1 is equal to 0, so we have 0 here. This will give us 0. 0 is less than t. We'll do the same thing where we move j down, right? We'll move j down. This is still less. Oh, sorry. We move j when the values are superior, right? So we begin to move I instead. So when we move I from here to here, 1 and 1, no, we don't do that. We move j instead. We move j down because we need to ensure that the values are less than the target, right? So since the value here is less than the target, we continue decreasing j. So when we move j from this point to this point, right, we'll have -1 and another 1 here, right? And the condition for shifting the pointers is such that I has to always be less than j, right? And by the time we move j from this point to this point, our loop will terminate, our iteration will end here, so we will no longer need to shift it. Now when you count the pairs that we've seen so far, right, here we have 1, 2, and then 3, which is the same as the brute force solution here by just incrementing the count by 1, right? Now to effectively find the pairs, right, to effectively count the pairs, we simply need to find the distance between j and I at the point where we found a valid pair. So meaning the count will be calculated this way. So we found a valid pair at this position here, so we'll just do j minus I. which is going to be equal to value. So this 0, index 0, 1, 2, and 3. So this is 4 here. J minus I is 3 minus 0, which is equal to 3. And when you count this again, you'll see 1, 2, and 3. So with this way, we can easily find the count for every valid pair, right? We can easily count the valid pairs in this array here. So we sort the array, and then we use a binary search with a combination of 2 pointers to find the valid pairs that satisfy this solution, this condition here, this condition, this here. So the sum has to be less than the target, the sum of a particular integer at I and j has to be equal, it has to be less than t, right, which is the target. Now the other thing to note is that the time complexity for this solution now has reduced, right? We are no longer using a quadratic time complexity like our brute force solution here. This is going to simply be O of n, because we are shifting the pointer for every value in the array. But due to the fact that we sorted this array before we started searching, this will actually have an effect on our solution. But I think if the array was sorted initially, then it is easier for us to find the pairs, right, without using a nested loop, which is our brute force solution. So the code for this would look something like this. So let's go back and write out the code from scratch. I'll come here, right, and then I'll create a new file. I'll create a new file here. So we have binary set trees. We want to sort, so I'll put it in 2 pointers. I'll create a revision folder. So revise. Okay, so here's my revision folder. Or what was I calling the folders for revision? Okay, repetition. All right, because I'm repeating it again. Okay, so let's rename this to repetition. Refactor, rename, repetition. Okay, so we create the file for this question. So this is the question here. Yes, so let's copy this, the file name, refactor, rename. Okay, so I'll create a new file here, new Python file, and I'll put this here, and I'll call this repetition 1. So this is the first time I'm repeating this question again. The idea is to continue repeating the questions until they really stick and you naturally understand and find similar patterns in other questions. So yeah, so here's what we need to do. I'll call this you know what, let me find out how I can get these questions boilerplate. I don't want to go through the other part. Let's see if we can see it here. Yep. So I'll copy this. Okay, so I'll paste this here. Now you can see this part. So alright, so let's start with this. I'll change this here to, so let me import this class, this module here. So we imported that. Okay, that's about it. Now here's what we need to do. First of all, we need to sort the array. So we'll say nums.sort. We sort nums. we take the first, so we'll create a count variable, and set the count to 0. Count is equal to 0, and we create I'll call this I and j. This will be 0. I will start from the beginning, and j will be the length, the last item in the array. So length of nums minus 1. Now we'll begin iterating, right, to find the values. So let's remove this part. So we'll say while the left is less than the right, while left is less than right. Oh, sorry, while I is less than j, while I is less than j. So here's what we need to do. While I is less than j, we need to start comparing the values. I don't know why this cursor is changing. Okay, so we say I will just I usually do this to find, I'll call this total. Total is just nums at I plus nums at j nums at j. Okay, so say if nums, if the total is less than the target, and I usually like catching cases like this. First of all, if the total is less than the target, right? So let's say here, if the total that we find at this position anywhere in the string is less than the target, then it means we found our pair, right? And we can count. Otherwise, if it is not, then we have to know for sure that our total is now superior to what we are looking for. So we need to reduce the right pointer, right? Now, in the case where the total is not equal to the target, we don't want something like that, right? We also need to reduce the right j towards the left, which is towards I, right? Otherwise, if it's superior, if the target is less than what j is, we shift I, right? Sorry, if the total is less than the target, we shift I. But I'll usually do something like this first. So if the total is superior to the target, and or the total is the same as the target, right? We also need to check for that. So I'll say if that's the case, then we want to reduce the right pointer, right? So j minus equal 1. Otherwise, it means it is equal, right? So meaning it is less, sorry. Otherwise, it is less than the target, right? So total is less than the target. Then we begin the to shift the left. So why I keep saying left? This is I. I is going to be, minus equal, sorry, plus equal 1, plus equal 1. And then our count will be the distance between the two. Now, before we calculate the count, we need to do this first. Sorry. Just type in. Come on. Okay, so we can just find the count plus equal j minus I, like I said, j minus I, and then we return the count at the end of the day. So the count will be returned from the function, so we'll say return count, and then let's print this. So I'll say my solution is going to be equal to the solution class. We'll create an instance of the solution class, and then we print this. We use a I'll use this test case here to find so We can use this test case here. Um, so print solution. We can see my solution dot count pairs. Okay, so first of all we sort, and okay, so let's do this. Sorry, count solution. Yeah, we missed the target. Target is 2, right? Target was 2, so we'll put in the target here. So let's see. Target should be 2. Okay, so let's run this again. And you can see our answer here is 3, which is the same as what we had in um, the other case. So I mean, I don't need to submit this anymore. If you want, you can come here. You can see this is the solution. So this is the same thing. You know what? Let me just run it out and see what the time complexity will be. I mean, what our runtime rank will be, because it changes from time to time. So um, so let's do this. I'll cut out this part. It's basically the same thing, right? So let's see. This question might be hard for you if you're solving it for the first time. Okay, so there's a wrong answer. What did I do wrong? So hold on. Okay, sorry, I did not. I didn't sort the numbers of the nums. The sort. Okay, so this should work now. Alright, let's submit this again. Okay, I'm still, fairly low, but there's still room for improvement, right? So we'll do that later. I can see something here. You see, the funny thing is, this is the same question, right? This is the same solution I provided. Well, this time around, it's funny because this is now faster. It shows that this was faster, and even though it's still the same, it's still the same solution, right? Um. Anyways, it doesn't really matter now, right? We can continue with the rest. Okay, so let's move on to the next question in the list. So let me check my table here. We have numbers of students unable to eat lunch. Now, this is a Q question that I solved before, so we'll go through it again and see how we can solve this question. Now, this is a very interesting question, and I really like it a lot. So we can solve this. So let's read through and see what's about. The school cafeteria offers circular and square sandwiches at lunch break, referred to by numbers 0 and 1 respectively. All students stand in a queue. Each student either prefers square or circular sandwiches. The number of sandwiches in the cafeteria is equal to the number of students. The students are placed in a stack. At each step, if the student at the front of the queue prefers the sandwich on top of the stack, they will take it and leave the queue. Otherwise, they will leave the sandwich and go to the end of the queue. This continues until none of the students want to take the top sandwich and thus unable to eat. You are given two integer arrays, students and sandwiches, where sandwiches at I is the type of sandwich the I students in the stack I equal to 0 and I is equal to the top of the stack, and students at J is the preference of the J students in the initial queue. Return the number of students that are unable to eat. Now, so here is a queue related question, right? So here is a queue related question, and I will just come here, right, and show you. So let's remove this part. We are giving a student. So this here is the preference of the student, right? The what the student wants, and this is the standard stack, right? So before I go through this, let me check if there are any questions. So let's refresh this. So our John, oh sorry, if I Vergy, you couldn't look at the runtime. Use big O. MS runtime. Use big O complexity to determine if your solution is optimal or not. Yeah. Okay. So what I was comparing is just the analysis LeetCode does on your questions, right? So somehow, the time complexities is not really related directly. I don't know how they do the ranking, right? I'm not really sure how the ranking is done, but when you look at this, you can have the same solution with different rankings. Now, I know I'll have to do my own time complexity comparison, but I was just, trying to compare to see what LeetCode will rank this question, right, or rate the question. Obviously, this is not going to be accurate. So, yeah, which is why I was looking at it. Um, Anyways, sorting the array, right, will increase the time complexity by O log of n, right? I think sorting algorithms take O n log n or O log n. Let me see. Let me check. What is the time complexity of sorting algorithms? So let's see. Yeah, so it's going to be O n log n, right? Which is, I don't know about this part. This is not okay. So this is, I don't know, shell sort, but anyways, this is going to take O n log n. Hence, this is my best resource for searching for stuff. So let's check this. So selection sort. Okay, this is an entirely different thing. But I know I've seen it that generally normal sorting takes O n log n, right? So we'll come it. I will learn about sorting later. But for now, I think um, the this sorting the array, right? Sorting the array at this point takes a bit of the performance, away, right? Or it usually has a bit of effect on how the code will perform. And here we are just searching with a normal two pointers by incrementing the pointer left and right. So this will run for every number in the array, which is going to be O of n time complexity. So O of n time complexity combined with a O of n log n time complexity will make up the entire code that that I wrote here, right? So I hope I at least provided a satisfactory answer to your question. Okay, so let me go back to the question we're solving, and we'll look into that as well. All right. So let me close this part. Um, okay, so here's our question. We are being asked. So this is a queue related question. I did queue I think a week ago, and I have not done any other queue question so far. But I really just want to go through this and keep an idea of queues in my mind, just not to forget the implementation of queues in general. So let's take a look at this question. And this question has a bit of logic to it. By a bit of logic, I really mean, uh, it is quite a natural thing that happens. And if you think about it in that natural aspect, then it becomes clear what the question is really demanding. And maybe there's a bit of challenge how to write the code, which is what we'll also look at in this case here. So here is what we have. We have a list of students, at least the preference of the students, right? So this here will be the type of sandwich the student prefers. So I'll put this here. Let's do this. And then I'll copy this part. Sandwiches. So this will be here. So this is the sandwiches that are available. So we have a list of students. Now this is not so what this I think this variable should have been called preferred preferred sandwich. So is you know what? Let's just do it like this. So it's really let me let me remove this part. Okay. So it's really a comparison of the preferred sandwich against what is available at on top of the stack, right? So even though each student has their preferred sandwich in the sandwich stack, they can't directly, let's say this student here prefers a sandwich that is squared. I think we have circular and square sandwiches, right? So the square sandwich is represented by 1, and 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 the sorry, hold on. The square sandwich is represented by 1, and the circular sandwich is represented by 1, and the square sandwich, sorry, oh, what am I saying? The circular sandwich, right, is represented by 0, and the square sandwich is represented by 1, or it represented with 1, however. So here's it. We have 0 and 1. Now this student here prefers a square sandwich, but currently at the top of the sandwich stack we only have a circular sandwich. So what happens is the student leaves the queue, right? Leaves the front in front of the queue and go back in the queue, right? So meaning this person will walk away and come back to the end of the line, hoping that the next time they are in front again, their preferred sandwiches at the top of the stack, because no students can draw or pick a sandwich in the middle. You can only pick a sandwich from the top of the stack. So this is like a natural order of how is this even natural? But let's say, when you think about it, it's just that if you don't find what you're looking for, hopefully what you're looking for is at the bottom of the stack, right? Or is still within the sandwich stack, then you need to go back in queue. But if what you're looking for is the same as what is currently at the top of the stack, so in the case where, let's say, so these first two students go back in queue, so they will go, this will go behind, right? So we'll have 1 0 0 and 1, right? And next time, because this student here, we are now at this point, this student here does not, it prefers a square sandwich, so we'll have a new queue that will look like this. So we'll have 0 0 1 and 1, right? Now, since we have, you know, the student in front now prefers a circular sandwich, which means they match, right? So meaning this student has to leave the queue and this sandwich is taken. Now at the top of the sandwich stack, we have a square sandwich, and this student prefers circular sandwiches. So the array, or the queue will change again, once again. So we'll have 1 1 and then 0, because this person goes back in the queue. So here's what needs to happen, right? And with this, we now understand that at the end of the day, after removing students and and adding them back in the queue, or removing them if they found their match, which is their preferred sandwich, then we'll be left to find if all the sandwiches have been taken, right? Or there are still students in the queue. If there are students in the queue, then we return the student, how many students are left in the queue. In the case where there are no students, we still return if there are no students. Now, how do we check if there are students in the queue? Well, if there are students that do not prefer any sandwich, right? Because in this case here, you can see every student will, there's a chance for all of them to have the sandwich they need. Because here, after removing this, one matches with this, so we remove this person from the queue and then go with this sandwich, and then our queue is now 1 0, and then we have 0 1 for the sandwiches available. Now, since the sandwich at the top of the stack is 0, this student does not prefer circular sandwich, so they go back in queue. So the queue becomes like this. So we have 0 and 1, right? So these students will take their sandwich, and this person leaves the queue, and the queue is left with just one person, and this person prefers a square sandwich, so a square sandwich is taken and this student leaves the queue. Now, in the case where there are students that do not prefer the remaining sandwich in the queue, let's say for example we have a circular sandwiches, and the remaining students are prefer square sandwiches, right, which is ones. So how do we return the number of students remaining to eat, or that are unable to eat? Well, it is actually, we can use what do you call this, a least comprehension method, right? And say for every student in this queue, right, in this queue, if any of them do not prefer the sandwich at the top of the stack, right, it means none of them wants to eat, right? So if that's the case, then we stop the iteration, we stop rearranging the students, right? If not, if we don't end it, we'll keep moving the students, right, these students here behind, and then this will come in front, and we'll keep swapping them, hoping they get their preferred sandwich at the top of the stack. But that's never going to happen, because there's no preferred sandwich for them, right? So they'll probably go hungry, and then we'll have to return how many students have gone hungry. So let's go ahead and solve this. I'll create a folder, a file for this question, and then we'll look at how to solve this. So wow, my time is up, but for the sake of this stream, I will increase the time to an extra 20 minutes. So let's just go with 25 minutes. Okay, so 25 minutes is fine. What number is this question? This question 1700. It's in the queues. So I've not solved a lot of queues questions this time around. You know what, let's first of all do this. Let's push this first question here. I'll say git add git git commit. This question was 2 pointers, right? So I'll put 2 pointers and this was leads code 28 24 and this will be, I'll just put this as 28 24 revision, right? I'll call this revision 1. So I'll put this like this. Okay. All right, that's been committed. Now let's find that was a 2 pointers question, right? So the new question now will be on queues. So I'll create a folder for queues repetition. So I will say repetition, right? Repetition. Oh, sorry, I want a folder instead of a file. New directory. So this is how I, revise my questions, solve them, more a couple of times. So the question number is number 1700. I'll just copy this, rename. I hate that noise. So I'll put this here and I'll say repeat 1. So this is the first time I'm repeating this. Okay, so I'll close all of these. So let's come here. All right, so with queues we know a few things, right? We have a few ways we handle stuff with queues. Now, first of all, to use a queue data structure, we use a deck module, or a deck module from the collections. Sorry, what am I saying? A deck class from the collections module, right? So if you don't know about queues, you can read some articles on queues that I have in my first video in queues. So you understand how queues really work. So we'll call this from collections. We import the deck. We import the deck class. Now you might be asking, why am I using the deck? Well, the reason why I'm using the deck is to just quickly be able to pop item from the front of the queue and then add them back to the end of the queue. So we can then, let me copy part of the function. You know what, I need the boilerplate to be able to solve the question, so I'll just copy this part. Let's copy this part and we can say this. So okay, we also need the list function, and let's import the list as well. Okay, so we'll create a queue of the students. So I'll call this student queue. query, and we use the deck class to create the queue. So the deck class, with the deck class, you simply pass in an iterable, and a queue will be created automatically. Now some functions will be available for us to use here, right? So we want to return um, the amount of students, or the number of students uh, that are unable to eat. Okay, so we created a queue of students. So meaning the number of students that are unable to eat will be the length of this queue, right? So the length of people left in the queue. So we can say while there are still students in the queue, while student queue, right? Then we can then say if the student, so the if this the first student in the queue prefers the sandwich at the top of the stack, then we remove the sandwich and the student, right? So say if students queue is equal to sandwich, is the top sandwich, right? Then we remove the student. So we remove the student from the beginning of the queue. So we say student queue dot. So there's a pop left that we use with queues that removes the item in front of a queue, right? And then we can just say sandwiches dot pop the first sandwich. So this removes the first sandwich from the sandwich list, or from the sandwich stack, right? So in the case where we have 4 sandwiches, we will be left with just one. Now the next thing we will do is else, right? Meaning they are not the same. The student does not prefer that sandwich. So what we do is we pop the student from the top of the queue. We remove the students in front of the queue, and then we add them back, so they go behind the queue. So this is going to be student queue, right? Dot so we pop left. So we append student queue, student queue dot pop left. So we pop left, and then we append that student back to the queue. So meaning if the student doesn't prefer the sandwich at the top of the sandwich stack, then they go back in the queues to join the queue again. So and that's what we do. And yeah, so for some cases this solution might work, right? So at the end of the day, we can just return the length of students in the student queue, right? So student queue, right? So let me show you how this will work for a very simple case. Now there are some edge cases we also need to handle, right? So we'll say I'll call this my solution, and this will be equal to solution. So we create an instance of the solution class first, and then we begin to use my solution. So I'll say my solution, okay, print the result of my solution dot count students, and then let's pass in to this first test case here. Because there are no students left in the queue, this solution here will work, right? So I'll paste this here, and then I'll copy this one too, and then I'll paste it here as well. Okay, so here's what we have, and let's run this and see. Now you can see we have 0, right? This is because I am sure there is at least there is a sandwich for every student in the student queue. Now in the case where there are some students that do not prefer setting the sandwich at the top of the sandwich stack, then we also need to check that as well. So we'll say if there is any student at all in the queue that does not prefer the sandwich at the top of the stack, then we have to stop the iteration, right? So we say if any student. So we can use any, and we can use a combination of any and a list comprehension, right? So with list comprehension, we can say we can return students. Let's say we return students, right? For students in uh, in in the students queue, right? So this will return every student for students in the students queue, right? And then we want to compare the value of these students here, right? What they prefer to the sandwich at the top. So if we say here equals to the students, sorry, the sandwich at the top, right? If any student, right? If any student, for every student in the student stack, in the student queue, sorry, if any students, and by student here will return either 0 or 1. If that value is equal to this, right, we can do something else. But what I'm looking for is if any student at all in this queue does not prefer um, the sandwich at the top of the stack, then we stop the iteration, right? So if I say if not any student, right? So if this is false, which means no student wants this, and we can just use not to, transform this to a true statement. Then we can say break, right? So break. Now before I do this, before I run this part of the code, I would like to first of all use a test case where this solution will actually break, right? So we'll take this. I think it will break in this case because there are 3 more students that did not have a food. So we'll run into an infinite loop, and we'll have to, break out of that infinite loop. So I'll put this here. Let me copy this. I'll duplicate this part. So let's duplicate this. So I'll call this here students and then sandwiches. My laptop will make a lot of, my PC will make a lot of noise now, but anyways, it is worth the try. So let's run this and see. Like you can see, this is still looping, right? The I had to like stop it, otherwise this will run forever. So with this, if you are here, you will hear my PC screaming. So with this, we can actually break out and stop the iteration. Right now, you can see we have three return. Okay, now that's good. Now the type complexity for this solution is going to be O of n. It's going to be, it's not going to be O of n. Yes, it's going to be O of n in a way, because hold on, I don't think this is going to be O of n, right? This should be O of n squared, because nah, it's not even O of n squared. It could be O of n, right, for every student in the queue, but then because the students are being attached back into the queue, so it's a variant value, the second part of this time complexity. I can say this O of n times m, right? So this will be the time complexity for this solution. So I will, O of n plus, if anybody has, okay, let me check the chat to see if anybody has an opinion of what the time complexity should be. Let's refresh and see what's here. So, well, I don't think nobody has any question. We do 9 to 5 ransom. So you work from 9 to 5. I mean, everybody has a time. I think the question is my current time compared to your time, right? I think that would be, so it is 8 p.m. here. So I don't know what time it is on your side. So 8 p.m. I think we are behind time also. Yeah. Okay, you did ask about time complexity. That's right. That's all right. All right. So let's continue with the question. So yeah, the question has been solved now. So I'll just simply push this to GitHub. Um, you know what? Let's first of all run this in lead code and see what it gives. So um, so let's see. If we run this again, it should work. Okay, I made a mistake. So this part shouldn't be here at all. At all, at all. Dun, 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 dun. Alright, what's this? Okay, test case passed. Let's submit this once again. Okay, yeah, as you can see, now this is a very funny thing. You can see the time complexity for this is really high, but the space is really low, right? But this same question I submitted, my solution is still similar to what I submitted previously, and you can see the time complexity for this. Or was that not what I submitted? So I don't think this really tells you exactly how good your solution is. So this is what I was talking about before, right? Yeah, it's basically the same thing. So, anyways, don't really beat yourself about this. It's just Let's Code doing its thing. So let's go ahead and add this to the solutions list. So git add git commit. I'll call this lead. Sorry, this is a queues question, right? Queues. Okay, and this is lead dash 700 1 700 and 1700, sorry, 1700 and revision rev 1. Okay, so that's it for that question. um we can go ahead and solve in the next question. So the next one here will be on trees, right? Yeah, so I solved this question before. So search a value in a binary tree, and then we can then search the range sum, right? After this two, I think the stream will be over. Um, Otherwise, I'll just solve one if my time is truly up. So I have 6 minutes left to explain this question. I can still go over it tomorrow, right? So uh, we'll have a look at that as well. All right, so let's see what we have here. So I can then so let me close this one, and this one I've done this already. Um, there is another one I need to do. Where is it? Okay, I wasn't looking at this. So binary search wasn't binary search. Okay, BS3. Because I solved the other question before, because I solved this question already, I would like to try. I would like to try this one instead, right? I would like to try this one instead so that I see how to do with this question. So let's go back to this. I'll go to the queues and created, sorry, a trees. So this is lead code 938. So I'll create a trees folder, a trees file for this question. So this will be trees, binary trees, and we'll call this, you know what, let me bring this here, and I'll create a file called lit dash 937, right? 938 range sum bst. Okay, 938 dash range dash sum dash bst. Okay, so let's read the question and see what we have here. Okay, first of all, let me check if there are any questions in the chat. Okay, you didn't ask any question. This guy is funny. So my neck is strong. Anyways, okay. So let's keep going. Let's keep it rolling, 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 rolling. All right, so we have 3 minutes left. Let me see. I actually read this question ahead of the stream, but I've not solved it yet. So, given the root node of a binary search tree and 2 integers low and high, return the sum of values of all nodes with a value in the inclusive range low high. Wait, did I read that well? Given the root node of a binary search tree and 2 integers low and high, return the sum of values of all nodes with a value in the inclusive range low high. Well, let's see. So here's what we've been given. This is our input tree, and the tree has some values here. Okay, and this is just unnecessary. I don't know why they do this thing, but anyways, so here's our tree. We are given a low and high, so meaning we want values within the low and high range values of nodes, and we return the sum of those values. So let's see how we can solve this. Well, first of all, the low and high, we can first traverse the tree. Aha. So we did tree traversal the other day. We can use a combination of tree traversal because we have to check each node in the tree. Obviously, we have to traverse the left subtree and the right subtree. So let me bring this here. I'll scroll up and take this tree here. Let's increment this part. Yeah, so this is our tree. This looks good now. We know traversing a tree in a pre-order form, right? Pre-order form, pre-order traversal. Pre-order traversal visits every node in the left subtree before visiting all the node in the right subtree. So we visit all this node of the left subtree, right, from the root, and then we continue searching from the right subtree, right. So we search all the right subtree values. Now we've been given 2 other values, which is the high and low, right. So we want nodes that have values within that range, right. So this is going to be, what's the high here? The high here is hold on. The high here is 15 and the low here is 7. So we want to find nodes that have values between 15 and 7. So I'll put 7 and 15. Okay. to stretch. So we'll use a pre-order traversal to find the values, right? So we'll start from the root node and search down the left subtree. We'll search the left, this, along the left side of the root node, and also this is also on the right side of the root node. So we search here, we search from this place, we'll check the values all the way down, and then we'll also check the values on the right hand side before searching on the right hand side of the actual root node, right? So we start here. First of all, the root node itself is within this range, right? The root node is 10, and we know 10 falls into the range of 7 and 15. So we can create a sum value, right? I'll put a sum variable, and then we add the values, right? So we have 10 plus, now 5 is 5 within this range, 5 is not within the range. So we go again, we search here. This is 3 doesn't fall in the range. Before we search 7, so 7 is in the range of 7 and 15, so we add 7 to this place, and then we come here too. So we have 15 here. Is 15 within the range? Now the reason why I said 7 is in the range, because the question says we should include the range, right? So the value in the inclusive range, so the range endpoint have to be if any value is equal to either the beginning of the range or end of the range, it's actually falling into the range. So we add those values into the range as well. So this 15, so we add 15 here, right? So this is 15, and at the end of the day, this will be equal to 32, because this plus this 17 plus 5 is 32. So 32 will be our answer. And because the reason why we don't choose 18 is because 18 is actually higher than 15, which falls out of the range. So we can use a combination of a pre-order traversal, because with pre-order traversal we can easily find the nodes, and the nodes that actually fall into the range, this range here, and use a sum variable to add those values to the tree. Now my time is up, and I'll provide the solution for this question tomorrow. Otherwise I will need to solve it now. Let me check the chat if there are any question. If there are no questions, then I will need to solve this question right away. Oh, hello, Uzbek. Uzbek is back. Nice to have you here. So let's see. Is Uzbek in our Discord server? You should join our Discord server to chat with others and ask questions if you can. Ransom is an expert in Python. So anyways, you can interact more with people on the Discord server. So let's carry on with the question and let's solve this. You know what, I will just attempt solving it. Now the reason why I'm so I actually, when you look at the okay, I actually closed this, so let's go back and find what I just closed. History, binary search tree. So let's see. This binary search tree question is actually kind of similar to what we are trying to do now. So we traverse each node in the tree, right? And now the funny thing with this question is that we are going to use a pre-order traversal, because we have to visit all the nodes on the left side or the left subtree, and all the nodes on the right subtree, right? So let's come back here and copy this. I will paste this here, and let's comment that we remove this part and this part. Okay, so first of all, we need to ensure that our root node has a value, right? So that's one of the things. We can have a tree with an empty root. So you say uh if root is none, if root is none, then we can just, okay, sorry, if root is none, then we return the sum of the values in the tree will be equal to 0, right? So we return 0. Now here is a pre-order traversal code. I think I have it here. So here's how the pre-order traversal works, right? So we can use a pre-order traversal to traverse all the nodes on the left subtree and then all the node on the right subtree. So we start here and we say if the root value, so we'll create a sum. I'll call this a sum. Sum is equal to 0. You know what? There's a sum value, so I'll call this node sum. Nodes sum is going to be equal to 0, and then we start by checking if the root dot value, right? If the root value is within the range that we are looking for, which is low and high, so we can just do it this way. I can say low is less or equal to the root value, which is less or equal to high, right? If that's the case, then we add this root value to our node sum. So the node sum plus equal root value, root dot value. Okay, so that's the first case. Now in the case where the root value is actually superior to the low part, right? It means we have to look into the left subtree to find all values that actually satisfy this condition here. So say if we had this, if low is less than the root subtree, so sorry, the root dot value, right? Then it means we want to look into the left subtree. So we'll use a recursive method here. In this case, we'll call the range sums binary set 3 here. We'll call this function again and just do this self dot, and we'll paste this here. Now what's going on here? What's that noise? I hint that with those noise. It's so annoying. Range sub 3, and then we'll pass it we can pass it the root. Now it will pass it root dot left, and you know, just the way we do pre-order traversal, we use a recursive method. We pass the left subtree, right? So this will recursively call for every node in the left subtree, right? And then we'll do the same thing here. So we'll say left subtree, we'll pass it the low and high, right? And then we'll do the same thing in this case. So if the high is superior to the root dot value, right, then we just call this function again. Instead of saying left here, we'll say right. Okay, so that's all we need to do, and I'll just return the sum. Once this is done calling recursively, right, we'll just return the sum. We'll return the node sum node sum at the end of the day. So we'll try this out and see how it works. No, well, let me try it directly in Lead code and see what this gives us. So let's run this and see. Probably something might go wrong. Okay, something went wrong. And what is it? My output is 10. Why am I returning 10? Root the value. Okay, so something strange is happening here. Maybe so return 0 if node sum is equal to 0. So okay, so this is interesting. The reason why it's returning 10 is because the iteration ended on the first node, because this recursive function is saying I should return node sum at the end of the day, which is not let's see what's going on here. So we check if low is less or equal to value, right? And we add the root value to the sum. This happened for the first node that we are seeing, which is the root node, which is why we have 10 here, right? And not 32. So I am not adding the other values in this case. What if I create a helper function that does the traversal for me, and then at the end of the day I just return that value, right? Because with the way we run a pre-order traversal, we pass in a node, right? And we check if that node is still there, right? If that node is not none, then we can then, recursively call the function and pass it the left or right subtree. So I think we can do that instead. I'll create a helper function. So I'll call this define pre-order traversal, right? I'll say pre-order traversal. Yeah. So here I'll pass it a node, right? I'll call this root node, sorry, tree node, and then I'll pass this. I'll say I'll call this sum, right? I can call this sum, and I'll call this sum. Wait, if I call this sum, right? Meaning, you see the way we make pre-order traversal. So in this case, I will not return anything yet. So if the node is there, then I can then return that node, right? So let's see. So with this helper function, I will still need to pass in the low and high. So let's pass it the low and high, and the sum, I'll call this sum here, right? Sum is going to be an okay, let's say sum nodes here. So in this case, I'll just call all these parts of the function. So I'll say if node, right, if there's a node, then we want to do this. We want to say So we say some node plus equal some node plus equal the current node, so node dot value, and then we do a recursive call to this. So we say self dot pre-order traversal, and we pass in the nodes left and right. So say node dot left, low and high, low, high, and then the sum nodes, and then we do this for the right subtree. So this is going to be right and sum node. Okay, so this is alright. And the next thing is, what's this? What is this thing here? Interesting. Anyway, so we recursively call this, we pass in the values, right? And so instead of, okay, so there's something else we need to do here. We need to check for the conditions, right? So we'll say if if node if node value, right? So I'll just simply do this. I'll simply say if node value is between the low and high, right? We'll just call this part. So I'll bring this here, paste. So instead of root, we have node in this function, so we call it node, and we call it node here. Okay. I call this some nodes. Okay. I'll say some nodes is here. Alright, so and then I can then pass this part to recursively call the left and right. So say if this, then we do this. Instead of root, this will be node, right? And then on the other hand, it will be this part here. So we can say if this, I'll just pass this here. Instead of root, we'll call this node. Okay, so we'll call the left side and the right side. So I'll remove this part. I'll remove this part and I'll just call the other function, and I'll say I'll create a new variable here. I'll call this sum. I'll call this total. I'll set this to be equal to 0, and then I'll pass this function here. I'll say self dot pre-order traversal. We'll pass in the root. We'll pass it the low. We'll pass it the high, and then we'll pass it total here. So we can then return total. So we just return total at the end of the day. Return total. So okay, so I can see what's this saying? It's just a warning. I mean, this sum here is going to be an integer anyway, so let's just put it there just to avoid some test cases. No, let's run this and see. I'll copy this part and let's just run this function once again. Okay, so wrong answer still. Alright, so there's 0 outputs. I mean, this should have added the values right into the node tree. Some node, what am I doing here? If node of value, hold on. Okay, so this is not supposed to be here. Pre-order load node. No, let me test it here before I put it on lead code. So my solution should be equal to solution, and then let's print the solution here. So print, we'll have to insert the nodes in the tree. Oh god, I don't want to do that now. So let's just do it this way. You know what, let's run this part again. I think I said if it's within this range, we want to add the values here, right? So so let's see what we can do. I will just copy this part here again. Let me post this. So if there is a node, right, we'll do a left traversal. I mean a pre-order traversal of the tree, right? Oh my god, what am I doing? Let me copy this part. I'll just copy this part again and properly. Yeah. So we have pre-order traversal as our helper method, right? And then some node we passed in. We just return the total at the end of the day after calling this function. Let's see. Okay, this is even worse than I thought. So what's going on here? Low, high roots. I mean, I'm traversing all the nodes in the tree. Node right. I mean, we need to traverse both right and left, right? So, I mean, there is no need for this condition here. If we are doing a pre-order traversal, right, we are surely going to visit every node in the tree. So, I don't think there's the need for this condition check here. I mean, as long as the values are actually equal, I mean, the value is within this range, then it should work, right? Let's run this again. Oh my god, my time is up, but you know what? No problem. No problem. Okay, another wrong answer. I don't know what's going on, but wait, so if we have some nodes here, it's an integer, we are doing plus equal. So if node is in the tree, okay, you know what? I'll look at this again. Literally up. Let's check the chat if anybody has a solution. Uzbekistan. I should come to Uzbekistan. No problem. I'll come. I'll come. Wow, that's really nice. That's really, really nice. Emmanuel said he's. Oh god, this is really funny. You two, you want to go? You want to go to Uzbekistan? I mean, I'll surely have. I'll surely like to come there one of these days. That's really nice. That's really nice of you, Uzbek. Um, yeah. Don't worry. One day we'll all meet each other physically. Yeah. We'll come to Uzbekistan. Everybody, even ransom. All right. I think I'll look back into this question tomorrow. So let me push the one I have done today. My time is up. I need to go and do something else. So yes, at Google. Oh, that could actually, happen, right? That can actually happen. Oh, sorry, I've committed. So let's just okay. All right, guys. Thank you for being here today. I'm really tired now. I have to go. We'll see.